All right, so welcome everybody. So it's a pleasure to have Deng today, who will tell us about local systems on special varieties have two-step nilpotent monodromy. So please go ahead.
Okay, thank you very much for the invitation. So it's my great pleasure to give a talk on some rational on fundamental groups of algebra varieties. So actually, this is based on a series of joint works with Cadorel and Yamanoi. So Cadorel was my previous colleague in Nancy, Yamanoi, professor at Osaka University, and Junyan Cao in Nice University, and Christoph Hacon and Mihai Păun. Okay, so let's start. So first, let me give some brief introduction to special varieties. So, so this was originally introduced by Campana in his program on the classifications of algebra varieties. So roughly speaking, this means that no fibrations onto a variety with orbifold base of genotype. So somehow, as a name, so this is opposite to varieties of genotype. So he called it special varieties. So quite far from being of genotype. And and he proved that actually why he used this, because he proved that for any algebra variety, or more general for some compact Taylor varieties, so it admits a fibration onto with spatial general price being spatial and the orbifold base being genotype. So in his program, he proved that one can always make such a decomposition, which he's called the call map, and this is maximal. So somehow. So the typical example is just since we're familiar. So the varieties with logarithmic Cadorel dimension 0 or rationally connected varieties. And an important thing to mention is that actually, so not like the people classify varieties with Cadorel dimension. So special varieties can have any Cadorel dimension except being genotype, as it cannot be genotype. So therefore, it can be minus infinity 0 to d minus 1. So d is a dimension of the variety. So it can be have all such intermediate Cadorel dimension. That's why people thought that Campana thought that this is important because it's not only it's more refined than this the classification using the Cadorel dimension. Okay, so this is some rough things. So let me give the more strict definition. First, let X be a log smooth projective pair. So here X is a projective smooth projective variety, and D is a simple normal crossing divisor. And let F be a algebra 5 space proper morphism onto a smooth projective variety Y, which with connected fibers. So if we pick any prime divisor delta of Y, so then you can write the pullback in the following way. And this is each EJ will map surjectively onto this delta, and also you have some F exceptional divisor. So FR is contained strictly in this divisor. And now you can define the multiplicity of this delta. So it will be defined to be if for F inverse delta, the inverse image was contained in the D in this boundary divisor, then we will say it's infinite. And if there's some component not contained here, not contained some EJ not contained in D, then you take the minimum of all such components. And now this is called the multiplicity of this base divisor with respect to this fibration and the log pair xt. Now you define the orbifold base of F is just you define to be 1 minus 1 over this multiplicity divisor and times this delta here, and you take the sum. So this is called the orbifold base with respect to this orbifold X and D and the fibration. And now, so let me make the convention. So in this talk, every variety is always assumed to be smooth. So if otherwise mentioned and defined and complex. So then we can make the following definition of what is the precise definition of special variety. So a quasi-projective variety X0 is called special. So if for any log pair such that the complements of D is birational, proper birational to this X0, and for every algebraic fiber space from F to Y, the orbifold base with respect to this XD and F, it's always not log genotype. So namely the Cadorel dimension of ky plus this orbifold base divisor. So it's always less than the dimension of the base. So this is the definition of quasi-projective variety to be special. And also there's a more general one for general pairs. So maybe D has some rational has some KLT components, not necessary to be both log canonical. But here in this talk, I will only consider quasi-projective variety. So therefore, this is sufficient for my purpose. And there's another definition coming from hyperbolicity. So X0, so this quasi-projective variety is called broadly spatial. So if there exists a characteristic dense entire curve, which is a holomorphic map, just a holomorphic map from C to X0. So it must be transcendental. And if X0 has such a holomorphic map, then it will be broadly spatial. So this will also contrary to broadly hyperbolic, because a variety is called broadly hyperbolic, then there's no holomorphic map, non-constant holomorphic from C to X0. So therefore, so it's also something opposite to broadly hyperbolic. You can imagine spatial is far from being hyperbolic. And a property, important property that has been spatial or broadly spatial. So it's a birational environment. So you take birational, proper birational models, or just it will always be spatial if the original one, or it's stable under ADA covers. So this is some basic property of spatial broadly spatial varieties. And conjecture, which is in the same vein as the Green-Griffiths-Long conjecture, says a variety is spatial if and only if it's broadly spatial. So namely, so in the algebraic setting, algebraic geometric setting, it will be equivalent to some existence of characteristic dense entire curves. So this conjecture is still quite open. And spatial varieties now is very active in these years. So people studied from several point of views. So first, the arithmetic geometry. So there was a conjecture by Campana says that a spatial variety, so it has potential dense of rational points. So we know that the Bunbury-Long conjecture says that the variety is defined over a number field. If it's general type, then the rational point must be contained in characteristic proper closed subset. And it's contrary to the Bunbury-Long conjecture. And another point of view is hyperbolicity. As I say, a spatial variety expected to have dense entire curves or just vanishing Kobayashi pseudo distance. But the thing which I want to talk today is on the topology. So just the fundamental group of spatial varieties. So this is a conjecture by Campana in 2004. He asked that a spatial variety made the conjecture a spatial variety has almost a billion fundamental group. So when I say fundamental group, is always say topology fundamental group. Here I explain the notion almost. So a group G is called have almost P. Be almost P if it contains a subgroup of finite index that has proper P. So here almost abelian means that the fundamental group has the finite index subgroup that is abelian. So I will always use this almost property P here throughout this talk. And a strong evidence to Campana's conjecture, so although the conjecture is still open, but there was a strong evidence was made by Campana in 2004 and Yamanoi in 2010. So they're proving the following result. So on a spatial variety or broadly spatial variety, projective variety. So here you have to assume the variety is compact. Any complex local system has almost a billion monodromy. So in particular, so if the fundamental group is linear, namely, so there's a faithful representation from pi1x to complex general linear group GLNC, so then the abelian conjecture holds, because in this case, you just take the trivial, take this faithful representation as this, you study this complex local system, which is a faithful representation. And then you show that the fundamental group must be almost abelian. So this was proved by Campana first for spatial varieties, and later by Yamanoi in 2010 for broadly spatial varieties. So based on some very nice result in nonlinear series, and it gives a strong evidence. So a spatial variety is equivalent to broadly spatial varieties here. But actually, so this is for projective varieties. So it's a long time. People also expected a similar thing for quasi-projective varieties. But actually in 2020, so with Cadorel and Yamanoi, so we found a counterexample that in quasi-projective case, so this fails, you cannot expect almost a billion fundamental group. So our original example is complicated, but here there's a more general example was given later by Aguila and Campana. So the example is very easy. So you take an ample line bundle on an elliptic curve B, and you remove the zero section, let X be L minus the zero section. Then it will be a C-star fibration over B. And one can prove that it's a log Calabi-Yau surface. The log canonical bundle of X will be trivial in this case. And then, if you look at the kissing sequence about this vibration, so it's the C-star vibration, so you have the following kissing sequence about the cohomology. So then you will show that since the C1L is assumed to be ample, so then C1L in particular is not zero, this will show that the cohomology of H1X is equal to isomorphic to cohomology of H1BZ. The cohomology of the group is the same. So therefore, this will show that the pi 1, you will have the pi 1 for pi 1x, we will have the following sequences here, the short exact sequence here. And it's not a split. So this is only a central extension of, pi 1x is central extension of the fundamental group of the fiber pi 1 C star and the fundamental group of the base. And this means that this it's a pi 1x is not a virtually abelian, not abelian, but it's a nilpotent group of class 2. So let me recall the definition of nilpotent group. So a finite generated group G is called nilpotent. So if it admits a central series, so the increasing series, such that for the graded quotient, it lies in the center of G, quotient Gi here. So if it has such a finite, if it stops finite at finite steps, so then it will be called a nilpotent. And the minimal in here will be called the nilpotent class. So therefore here, what I say is a nilpotent of class 2 because it's only have two steps. So the first one here and the last one is here. They are both, it is a non-trivial extension of two abelian groups here, pi 1x here. And we say a G is called at most, or just I say simply say n-step nilpotent if its nilpotent class is less than n here. And in this talk, we will focus on two-step nilpotent. And now, so based on this example, so we revise Campana's original conjecture as follows. So we'll call it nilpotency conjecture rather than abelian conjecture. So namely, a special quasi-projective smooth variety will have almost a nilpotent fundamental group rather than abelian, almost abelian fundamental group. And so I recall a very classical question originally raised by Campana in 1995. He asked for compact Kähler manifolds, but later for also quasi-projective. So the question is the following. So if X is quasi-projective and pi 1x, if it's nilpotent, must it be two-step nilpotent? So that's quite amazing because at this moment, people cannot prove it. And also they cannot even find any example which is nilpotent, but with at least three-step nilpotent fundamental group. So still open. And so inspired by this question and by the example, it's two nilpotent. So we propose the following two nilpotency conjecture, which is a refined version than this nilpotency conjecture. So the statement is a special quasi-projective variety has almost a two-step nilpotent fundamental group. So namely, so you see that the two-step, if this conjecture is true, then it's sharp, as we know about the example we have. So they have two-step nilpotent fundamental group. So this is the version which I strongly believe that it should be true here. And now let me explain the main theorem I want to talk today. So the first one is a theorem by Cadorel and Yamanoi. I joined with them. So let X be a special or broadly special quasi-projective variety. So then for any complex local system on X, it has almost a nilpotent monodromy. So in other words, so in particular, if the fundamental group of pi 1x is the faithful representation of pi 1x to G and C, then the nilpotency conjecture holds in this case. And yeah, this is the remark here. But the proof is quite involved actually. So we wrote a long paper, and now it's split into 3 papers. So in the first 2 papers, we have to prove in some hyperbolicity result, and then based on this hyperbolicity result, we then prove this theorem. And also for this hyperbolicity result, we have to prove in some first develop some harmonic map to Euclidean buildings, so extending the previous theorem by Gromov-Shane. So this was done previously with Boatbeck, Daskalopoulos, and Chicago Mess, which is purely analytical things here. I will say it later. And so here you see every statement here is about complex local system, but actually, if in the positive characteristic local system, the things became simpler. So in 2024, with Yamanoi, we proved the following theorem. So X is the special, broadly special quasi-projective variety. So then any local system in positive characteristic on X has almost abelian monodromy. So here you see the things became quite different. So in complex local system, you have some counterexamples. The abelianity conjecture does not hold. But actually, for representation of fundamental groups in positive characteristic, so it means G and K, where K is the field of positive characteristic. So this conjecture still holds. So it always have almost a abelian image here. And okay, so this is something intermediate. But my final goal of this talk, I want to report recent work joined in progress with Hao and Hacon and Păun. Actually, we confirmed the two-step nilpotency conjecture in the case of in the linear case. So, but let X be a special quasi-projective variety. So here we cannot say anything about broadly special. So then any complex local system X has almost a two-step nilpotent monodromy. So in other words, so if X pi 1x is complex linear, so then the conjecture holds in this case. So this is the theorem which I want to talk later. So. And the proof is much more involved. So even so, I mean, with Cadorel and Yamanoi, we proved the nilpotency about the local systems on special or broadly special varieties. But actually, passing to nilpotent to two-step nilpotent, so there's still a lot of work to be done. I mean, we have to develop some deformation theory of local systems on quasi-compact Taylor manifolds. So using some Hodge theoretical analytic methods for these local systems. The main difficulty is that for quasi-compact Taylor manifolds or quasi-projective varieties, so we don't have the usual Deliba lemma like for local systems that by Simpson or the classical one by Delinis or Delin, Morgan, Sullivan. So we have to work very work in some difficult analytic things to do that. So any questions at this moment? Okay, so I continue. Now, I mean, let me explain the main idea of the proof of the nilpotency theorem for local systems. So actually, this, as I say, this is based on some hyperbolicity results. So we have to first prove in some hyperbolicity, and then we reduce the proof to this result. So the theorem is the following. So let Y be a quasi-projective variety. If there is a big and a heuristic dense representation from pi Y to GC with G be semi-symbol, then Y is of log genotype and pseudo broadly hyperbolic. So in other words, so there exists a proper closed subvariety Z of Y such that all the entire curves has image in Z. So namely all the non-constant holomorphic maps from C to Y, it must factorize through this proper subvariety. I just recall the definition of big. So big is which is called generic range in Cora's book or his paper. Say if a representation is say big, so if for any closed irreducible subvariety Z of X passing through a very general point, then the image of pi 1Z to pi 1X on the row must be infinite. So this is called the representation will be called big. And let me, so since this is not the main goal of today's talk, so I just quickly explain the rough idea of the proof for this result. So there are three cases about the things. So first, sigma is rigid or integral, and the integral. So namely, rigid means that any small deformation of this representation is still conjugate to this sigma. So integral, then it must define over some number field. So integral means that it factorizes through the GOK. So OK is this into the ring of integers. So in this case, so one can prove that sigma is more or less integral variety of Hodge structures. So in this case, using some analytical methods, just computing the curvature computing of the pure mapping, so one can show this whole. 不要再跑了。And then the second case is rigid and non-integral, and the third case is non-rigid. So non-rigid means that it can deform to non-trivial ones, non-isomorphic ones. And for the second and the third case, actually, one can show that there exists some, we will reduce things to non-Chemidian setting. So there exists some big characteristic dense and also unbounded representation from pi 1 x to gk, where g is almost a simple algebra group, might not be the same as the original one, and k is non-trivial local field. So so just the QP of characteristic 0. So now finite extension of QP. And now the next step is non-trivial. So we have to use harmonic maps or pluriharmonic as to Euclidean building. So this Euclidean building is associated with this G, some Varieties building of this G defined over K, and associated with this rho. So we prove the existence of pluriharmonic maps. And using these pluriharmonic maps, one can find a ramified Cadorel covering, which I call it spectral covering, expect to X. So one can show that because this condition, big, characteristic dense, and unbounded, this will show that this X spectral covering, XSP, is of log-Jones type. And now, one can also show that it has maximal quasi-Albanese dimension. So in other words, its quasi-Albanese map is generically finite onto the image. So then, based on some very complicated nonlinear theory, one can prove that the Green-Long conjecture holds. So in other words, because it's log-Jones type, then we can prove that it's pseudo-Brody hyperbolic. And the last step is much more complicated. So we have the key step is, because it's a ramified covering, hyperbolicity and positivity is not preserved under the ramified covering. So we have really spread the hyperbolicity from the spectral coverings, the ramified covering to X, and also general type to X. So here we're really using some properties of this ramified Cadorel covering. It's not arbitrary, so it's really related to these harmonic maps. So then we just first prove hyperbolicity from the spectral covering, then spread to X. So this is a rough idea of to proving the hyperbolicity of X if there is some fundamental group, the representation of fundamental group. So although the theorem statement is always in C, but here we really need to pass into some periodic field here for the representation. Okay, so now I want to show the nilpotency theorem if we to reduce this to the hyperbolicity theorem. So now let X be spatial or broadly spatial. So I want to prove that for every representation of pi 1 x to G on C, the image is almost nilpotent. Okay, so just if this is faithful, then this means the nilpotency conjecture holds. So let me first show that the characteristic closure is solvable. So to prove the image rho is almost nilpotent, we just want to show the characteristic closure because G on C is the algebra group. So if you take the image, we take this characteristic closure, it still be an algebra group here. We want to prove that the G is nilpotent group, and first we prove that it's solvable, and assume that it's not solvable. But we know that the solvable, then you take the radical, RG, the radical. This is the maximal normal subgroup, normal connected solvable subgroup of G. So this is somehow the obstruction to G to be semi-symbol. So therefore, when you quotient this radical, so G quotient RG, it will be a semi-symbol algebra group. So if G is not solvable, then this must be a positive dimensional algebra group. And let us take the composite of rho with this quotient. So we take the representation of rho to pi1 to pi1x to GC, and then the quotient together with this quotient, we have a characteristic dense representation. But the point is that it's not a big in general. So, but there was a theorem by Campana and also by Kola in their work on the Shafaric maps. So so although this is not a big, but actually if we replace x by some finite eta cover or some birational modifications, so it always factorized through some big representation. So there was a dominant morphism with general fibers connected from x to y f, such that this representation sigma is some representation of pi1y to this semi-symbol algebra group. Just to pull back, the tau is this one. So it's because sigma is characteristic dense, so therefore tau is also characteristic dense, and tau is big. It comes from Campana and Kola theorem. So now we are in a very nice case because here we have a base of positive dimensional, and there's a big and characteristic dense representation in a semi-symbol algebra group. By the hyperbolicity result, we can show that Y is general type and a pseudo-Brody hyperbolic. So in this case, so X cannot be special because it's by the definition, if X is special, then Y cannot be log general type. So, and also if X is broadly special, it has characteristic dense entire curve, then you take the composite with F, Y must have the characteristic dense entire curve, so contradicts to pseudo-Brody hyperbolic. So by the assumption X is special and broadly special, we get the contradiction. So in other words, G must be solvable. It is equal to its radical. And now the interesting thing is that how can we pass from solvable to nilpotent? So there's still some work to do. So here I will sketch it. So actually, so we first consider the following exact sequence. So for a solvable group, if you take the unipotent radical, so which is the maximal normal unipotent subgroup of G, so let me denote U to be this unipotent radical. So then we have the following short exact sequence. Then here T is the maximal torus of G here. And there is a nature action from T to U quotient U prime. So U prime is a commutator of U. So therefore, so U quotient U prime. So this is a abelian group. And a criterion says that if this action is trivial, so this T, the conjugation action of T to this abelian group, if it's trivial, then G, this short exact sequence G splits. So namely, it's a trivial product of the torus with the unipotent group. So therefore, it must be nilpotent. So this is the thing we will use. We want to show T here acts trivially on this U quotient U prime. But how to do that? Now we have not used the property of special varieties. So we will relate this action to the monodromy of the variety mixed Hall structure coming from quasi-Albanese map. So here X is special. So we want to prove that first we prove that for broadly special variety. So this quasi-Albanese map is always dominant with general fibers connected. And moreover, the following exact sequence is we have the pi1 exact property. So namely for general fiber F of this quasi-Albanese map, we have the following short exact sequence here. So in general, I mean this one is coming from automatically because X to Y is dominant with general fibers connected. So the main point is that this exact sequence here. So in general, so this coming really from the property of the special varieties here. So roughly speaking, so just loosely speaking, so here this is like that A behaves like a smooth vibrations because if this is a smooth vibration, we always have such a short exact sequences. So therefore, because if you consider the variety mixed Hall structure, you really have to consider to the smooth locus here. But by the short exact sequence, pi1 exact sequence here, you can moreover consider something extended since over the whole base here. So then we're using a theorem by Deng, which he proved that for the algebraic monodromy group of the variety mixed Hall structure. So this means that the characteristic closure of the monodromy group, So this is the definition of eligible monodromy group, has unipotent radical. And we related this monodromy related to the Deng theorem, and one can relate this action T to the action automorphism of U quotient U prime. So by the theorem of Deng, we can prove that this will factor through a unipotent group. But now there's a lemma. Is the lemma says that for torus, algebra torus to the unipotent group in characteristic 0, it must be trivial. So in other words, so this shows that the action is trivial, and therefore by the criterion we have seen before, G splits as the product of the unipotent radical and the torus. So therefore G must be unipotent. So somehow this means that we're using hyperbolicity first to show special varieties or broadly special varieties. The monodromy must be solvable, and then using more involved geometry of special varieties together with the Deng theorem to show that from proof solvable is more of a nilpotent in this case. So this completes the proof of the first part. So we prove that the nilpotency theorem for local systems over special or broadly special varieties. So now I will stop a bit because I will using this result we can give a new proof of Campana and Yamanoi's abelianity theorem for projective special varieties. This is actually more evolved than their original proof, but it has an advantage that help us to understand the two-step nilpotency theorem. Okay, so to do this, so I will just give some fundamental result, I think, in Hodge theory, which I call the one-step phenomenon. So actually, if we using Deng and Goldman-Milson's deformation theory for local system or representation of varieties of compact Taylor varieties, together with Simpson's non-binary Hodge theory, so we have the following one-step phenomenon. So the theorem is the following. So let H be a holomorphic map between compact Taylor manifolds X to Y, and let V nabla be a semi-simple flat bundle on X. And let me denote rho to be the monodromy group, monodromy representation of this semi-simple flat local system. And if the first thing, if the pullback of this rho over Y is a trivial representation, and the second one, so if for the H1 cohomology of H1 from X on the morphism V here, because V is a semi-simple flat bundle, you can define H1 here using the Drum using both either Drum or local system definition, so they are the same. So you take some Drum resolution for this on the morphism using this flat connection. Drum complex, you can define the first cohomology. And if you pull back, you have the following scene. So the assumption is that the pullback of H1 is 0. Under these two assumptions, then one can prove that for any deformation tau of rho, the pullback of tau is always trivial. So this means that for every irreducible component in the variety of representation containing rho, so its image on the H star is a point just. So it will be constant. So the restriction of H star over the variety of representation, the component containing rho, so it's just a constant over here. So this is which I call a one-step phenomenon. So because the first order deformation, so this is so if you are familiar with Goldman-Milson's theory, so H1X on the morphism of V. So more or less, this is just the tangent space of this in the character variety of Pi1X to G and C, somehow like that. So namely, the first order will determine the first order vanishes. Will say that every higher order will vanish. So this is the philosophy here. So which I call one-step phenomenon. And now I want to use this one. So for the proof, so using some Hodge theories, so one can do that. And now I want to using this one-step phenomenon together with previous nilpotency theorem to give a new proof, but more complicated proof of Campana and Yamanoi's theorem. So okay, so now starting is that let's take any rho representation X is projective, which is special or broadly special variety. our goal is want to prove that the image is virtually abelian. So actually, we are free to replace X by finding the guitar cover. So then we just say the image is abelian. And as I say, by our nilpotency theorem, so rho decomposes as a product because the thoracic closure of rho is just a nilpotent group, which is unipotent times the abelian times the commutative algebra tori. So therefore, rho is a product which is a abelian representation and a unipotent representation. So to show that the image of rho is unipotent, so then we just try to prove that the image of rho is trivial here. So I mean to assume that the rho is unipotent because we don't need to consider the abelian case. Now we assume rho is unipotent representation. We want to prove that in this case this is trivial. And now by the Albanese, so first, by our previous work, we know that the Albanese map is pi1 exact. So namely, we have the short exact sequence from the general fibers to X and to A, and let F be a general smooth fiber. Utah denote this inclusion. So now, as this is a fiber of the Albanese map, so the pullback of H1 will be vanishes identically. So it's trivial. But actually, if you take a trivial flat bundle of rank n, so let V nabla be a trivial flat bundle. So then, if you take the pullback of this H1 of this trivial flat bundle, because this is just a trivial flat bundle is just the direct sum of C. So then the image here will be trivial here if you take the image here. And now so it means that the image here is trivial. Okay. Then by U is unipotent. This is deformation of the trivial representation, which is just the monodromy of the trivial flat bundle. We using the one-step phenomenon. We show that the image of rho here restriction on the fiber, general fiber, it will be trivial by the one-step phenomenon. It's the same as rho zero, because when you pull back the representation to general fiber F, it will be always trivial here. And now by the short exact sequence here, so rho will factorize through because the rho restriction to pi1F is trivial, and by the short exact sequence here, it will factor through the pi1A, which is a abelian, it's a abelian group. So therefore, rho has a abelian image. So this shows that for every unipotent one, so it must have a abelian image, so then it must be trivial. And this proves the abelian conjecture. Why we can pass from nilpotent to abelian in the projective case. The underlying principle is as far as I say, it's just the one-step phenomenon. So you don't have some higher order classes in the nilpotency because of this. When you restriction rho to this to the pi1F, it will be trivial. So therefore, you have no higher extension classes here. And now, so this is a one-step phenomenon, and I want to use similar ideas to show our two nilpotency theorem. Just means a special, just a refined previous result. So for a special variety, so we cannot say anything about broad special. We want to show for special varieties. So the local system have two-step nilpotent monodromy. But here, I mean, for quasi-compact Kähler varieties, so the point is that the one-step phenomenon fails. Instead, we have the two-step phenomenon. So let me state it. It's actually the original theorem is much more involved. I just extracted the simplest version here. So if you are interested, so you will see our preparation soon. So just look at the paper later. So let X be a quasi-compact Kähler variety. So a quasi-compact Kähler means that it's a Tarski open subset of a compact Kähler manifold. So then there exists a local system, a Vn, with two-step unipotent monodromy. So such that for every extendable holomorphic map from Y to X from a quasi-Kähler manifold. So here, extendable means that this holomorphic extends to the Kähler compactifications of Y and X. So I say extendable holomorphic map. Namely, it's not some transcendental one. If the pullback of this local system Vn by H is constant, this local system on Y is a constant local system, is a constant system. Then for every deformation of rank 1 trivial local system, tau it will be its pullback will also have trivial monodromy. So I mean here is unlike the one-step phenomenon because one step means that you have actually you just check the abelian case the H1 suffice to give all the information. But here you have to check for the local system with two-step unipotent monodromy. So for this Vn, the construction is complicated. So it's really somehow in this in the complete local ring. It's in the how to say in the comes from the complete local ring in this variety of representation of pi1y. So and now for this theorem, so the proof is involved because we have to explicitly constructed a canonical universal connection. So I mean, because if we want to see why H star tau why H star Vn vanishes, it will imply H star tau vanishes. I don't see any abstract method so can achieve this. So because previously we have some result by Han and Zhak on some unipotent variation of Hodge structures, unipotent variation of mixed Hodge structures. But I cannot see anything about a two-step, one-step phenomena from their paper because this is more or less some general constructions. So to prove our theorem, we really have to make this local system explicit, and we do the computation. We show that two-step vanishes suffice to show everything vanishes here. So I will not list it as the main proof and the strategy, but I just want to take it as a package to prove our two-step nilpotent monodromy result. So now let me prove the theorem. So so let rho let X be a quasi-projective spatial variety. So let rho be a linear representation. So our goal was to show that rho pi1x is two-step nilpotent. So first, we want to prove a technical result. So the result is the following. So since X is special, then one can show that for the quasi-algorithm map A of X to X, so a general fiber Y of this quasi-algorithm map is also special. So originally, so when X is compact, this was proved by Campana and Cadorel in a paper. So they call it stability of specialness property. So somehow means stability is preserved for take the fiber of the quasi of algorithm maps here. But I think it seems that this is an isolated result. But actually, when I was considering this problem, I found that it's really related to the scenes we are working here. That's very nice to see. We have some nice application of such a result. Now we want to, as I say, we want to prove that rho is a two-step nilpotent because the rho splits as the product of abelian one and unipotent one. So we can assume that the rho is unipotent. So so as we prove that so Y is since a general fiber Y is special. So we consider first the quasi-algorithm map of Y. So we could again the next quasi-algorithm map of the fiber of this quasi-algorithm map of X. So it's also pi1 exact by our pi1 exact theorem. So now let F be a general fiber of this quasi-algorithm map. I did AY here. So a key step, as I say, so we have to show that because gamma n, Vn is very explicit. We wrote it in an explicit way. So one can show that when you restrict this Vn, this local system, which given in the two-step phenomenon, when restricted to this F, it will have trivial monodromy. So it becomes a trivial local system. When it restricts to the fibers of quasi-algorithm map and take again a fiber of the quasi-algorithm of the fiber, so it will have trivial monodromy. This step is really related to this expression of this constructed two-step local system. And by this two-step phenomena, so since rho is unipotent, it's a deformation of the trivial representation. Okay, and the trivial and therefore, so this will be trivial. So when restriction this unipotent representation, its restriction to F will be trivial. And now, by pi one exact sequence of this quasi-Abelian map of Y, so we have this short exact sequence. And if you take a restriction of rho to pi one Y, it will be trivial. So this means that it will factorize the restriction to pi one Y will factorize through pi one AY. So then it has a abelian image. So now you consider the original quasi-Abelian map again. So the restriction of rho to pi one Y is abelian. So in this case, so you can show, okay, you take the quotient of pi one x, rho pi one x, quotient of rho pi one y. So it will be abelian because pi one a is abelian. So this means that rho pi one x is two-step nilpotent in this case. So this is a rough idea of the proof. But actually, you see from here, you did not really see why the interesting thing. Why? So we have this very mysterious two-step phenomenon. Why? So when you take two-step quasi-Arrhenius map, then the local system becomes trivial here. So this really I cannot write the formula here. It's too complicated here. And now I ends with the following question. So as we know, so for broadly special varieties, we can also prove that the nilpotent local system on broadly special varieties also has nilpotent monodromy. So I want to ask whether two-step nilpotency theorem holds for broadly special varieties. So this we still work on that. Did not have some idea on that. So okay, so I stop here. So thank you.
Thank you so much. Any questions? So let me ask a big question. So do you have a sense, I mean, how much much more you would need in order to treat the Brody case?
I think we just want to show. I think we want to show similar result like this one. So I don't really because if X is broadly special, so I just only need to show for general fiber Y of this quasi-Abelian map is pi one exact. It's Albanese is pi one exact. I wanted this result. So because because X is special, we prove that Y is general fiber Y is also special. Then we use in pi one exact of specialness. But I just needed this one because for broadly special, we don't know how to show the general fiber is still broadly special or special. So therefore, we don't know how to prove this at this moment. So this is the only point we need. Yeah.
I see. I see.
So maybe just some vague questions. So in general, for these special varieties, there's some quasi compact or maybe quasi-projective ones. So do we know this Albanese map is also like surjective or
No,
something?
it's just a dominant. It's in general not subject dominant with general fibers connected. So
Yeah. Okay. Yeah. I mean. Yeah. Okay. Yeah.
it's not proper. It's not proper in general.
Yeah.
So.
Sure. Sure. Okay. Okay.
Yeah, yeah.
Mhm. But it's not like a locally trivial kind of vibration thing, or
No, it's not local trivial vibration. So, uh, I don't think in general it's locally trivial. So, I did not try to find example, but I think for special varieties, the quasi-Albanese map, we have a structure theorem which says that actually the quasi-Albanese map for if rho here, if rho is bigger. So I think one can show that the quasi-Abelian map, a general fiber is also birational to some semi-abelian variety. So I mean, it means that it's a vibration into semi-abelian varieties over some semi-abelian variety, birational to something like that. So if rho is linear, so somehow you can manage use such a structure here.
Mhm.
Yeah, but I don't think the general fibers, two fibers will be isomorphic. It might have some deformation of the general fibers. Yeah.
Mhm. And so at the beginning, you mentioned that this Cadorel dimension can be anything in between. What were the examples?
Yes. I cannot remember. So I think so we constructed some example in quasi-projective cases, which is birational. I think it's birational to some semi-abelian variety, but with Cadorel dimension 1. It's not proper birational. So I mean, to some semi-abelian surface, X is a birational to A. A is a semi-abelian surface, and kappa bar A is equal to 1. This is a birational. So we can prove that it's special, but not a. There's some even broadly special. There's some metric. There's some topology density entire curve, but it's not a. Yeah, it's not a Cadorel dimension 0. So
Okay. Yeah. Maybe just one more question. So at the end, you kind of take this quasi-Albanese map of the fiber again. If you take that fiber and then take the quasi-Albanese map, do you get something again? Or I mean, if you just iterate this quasi-Albanese map and then take the fiber, which is special, and then you take the quasi-Albanese again, does it stabilize?
Yeah, exactly. Because of the theorem. Because of the theorem, each fiber of a special variety, you always have the general fiber special. So therefore, you can't iterate it. It's always special.
Okay, so maybe my precise question is that since you have a two-step nilpotency, does this process stabilize after the second step?
Yes, exactly. I mean, here, because if you restriction to this one, it will be abelian. So if it's to abelian, then it's always abelian. I mean, somehow, because if you take the fiber of this Albanese, so this is the fiber of the Albanese map of X, quasi-Albanese of X. So if you take any row is nilpotent, so then it will be abelian. So therefore, if you take further one, it will be abelian.
Okay.
Yeah,
thanks.
you stop. Yeah, you stop somehow. You stop at the second step somehow. Yeah. And for Pi1F, because you do it again, then it will be trivial somehow. Yeah. Sorry. No. Yeah, it will be trivial because this is abelian. When you're abelian, you take some abelian representation. All the abelian representation will be trivial on the Albanese. Yeah. Yes. Right. It will be stopped over this second step. The representation will be trivial in this case. Yeah.
Okay. Thanks.
Yeah, you are welcome.
Other questions or comments? Okay, if not, thanks so much again for the talk.
Okay, thank you for your attention. So, thank you.